Hello, dear students. So, this lecture is in continuation with the last lecture that was based on modeling of EEG signals. So, today we will discuss about the autoregressive method. In last lecture, we have seen the linear prediction theory which can be used for this AR method. This is a stochastical model which can be extremely useful in the representation of certain practically occurring series. So we are calling it as autoregressive, and also it is generally represented as AR model. In this model, the current value of the process is expressed as a finite linear aggregate of previous values of the process and a shock epsilon n. Now let us denote the values of a stochastic process at equally space-time spaces n minus 1, n minus 2, and we are representing it by yn. So we have the time representations of yn as y of n minus 1, y of n minus 2, so on. So you can see the equation number 1, that is yn equal to alpha 1 y of n minus 1 plus alpha 2 y of n minus 2 up to alpha p y of n minus 3, and in this we are adding epsilon n, that is a shock parameter. So this is a AR process of order P, and why we are calling it as a linear model, as this can be given by the equation as you can see in number 2, alpha x1 plus alpha x2 up to alpha p xp plus epsilon. Now we can relate a dependent variable y to a set of independent variables x1, x2 up to xp plus an error term epsilon is often referred to as a regression model, and y is said to be regressed on parameters x1, x2 and so on up to xp. So equation 1 here, the variable y is regressed on previous values of itself. So this model is autoregressive. Now by taking the z transform of equation and obtaining the transfer function for this AR process, we can represent it as yz by epsilon pz, which is equal to 1 by 1 minus alpha 1 z inverse minus alpha 2 z inverse 2 up to minus alpha p z inverse p. We can also show in this figure. So alpha pn is nothing but white noise sequence, and we have a EEG signal that is represented as yn, or in z transform if you say it is yz with the transfer function of hz. So in this representation we can see that EEG signal can be viewed as the output of a filter which is characterized by the parameters alpha 1, alpha 2 up to alpha p, and sigma epsilon p square is in practice have to be estimated from the data. The additional parameter sigma epsilon p square is nothing but the variance of white noise process epsilon p n. Incidentally, equation 1 is referred to as a Markov process of order P. So AR methods, which include the autocorrelation, covariance, modified covariance, Berg and recursive least squares, are closely related to the linear prediction methods. Now let's suppose first we consider a Markov process of order 1. So we can write the equation as yn equal to alpha yn minus 1 plus epsilon 1n, because here now p is 1 because we are talking about the process of order 1. So the parameter alpha and sigma epsilon p square now have to be estimated based on the past sample values of yn. If we multiply equation 4 by y of n minus 1, and if we take the expectation, that is a mean, So you will get, if you see equation number 5, that is expectation of the product yn into yn minus 1, that will be alpha times expectation y of n minus 1 to y of n minus 1 plus expectation epsilon 1n into y of n minus 1. So as we know that epsilon and y of n minus 1 are not correlated, so the expectation of the product will be 0. So this equation 5 will be reduced to, if you can see equation number 6, the second part on equation number 5 will be 0. So you will get expectation y of n to y of n minus 1, that will be alpha times of expectation y of n minus 1 to y of n minus 1. And if you write, this is nothing but the autocorrelation functions at time lag 0 and 1. So from here we can calculate this parameter alpha, which is nothing but the autocorrelation with time lag 1 divided by autocorrelation at time lag 0. So RY1 and RY0. So the above equation is nothing but it is identical to, if you remember, we have discussed the same similar kind of equation in linear prediction theory. Here there that was instead of alpha it was A, and here we are taking alpha, so it is nothing but the similar kind of equation. Now for computation of this variance, we have to multiply both equations by yn, and again we take the expectation, so you'll get expectation now yn to yn is equal to alpha times expectation y of n minus 1 into y of n minus 1 plus expectation epsilon 1n to yn. And from this we can say, now as we know this equation, yn is nothing but alpha y of n minus 1 plus epsilon 1n. If we keep this equation in equation number 8, so we can get that Eyn into yn is nothing but alpha expectation Ey of n minus 1 yn plus alpha times E of y of n minus 1 epsilon 1 n plus expectation epsilon 1 square n. So again, as we know that epsilon 1n and y of n minus 1 are not correlated, so again the second you can say the second term will be 0. So that equation number 10 now will reduce to expectation yn to yn, which will be equal to expectation alpha times expectation y of n minus 1 to yn plus expectation epsilon 1 square n. So in terms of, again in autocorrelation, if I want to write, so this Eyn into yn is nothing but, as I already I mentioned, this is autocorrelation at time like 0, and the second term after equal to, you see this first term, this is nothing but alpha times, we can write this as autocorrelation at time like 1, and this expectation epsilon 1 square, and nothing, it is nothing but it is again the variance which I want to predict. So we can calculate this value, and if you substitute back the value of, we can write in terms of RY1. If you write RY1 in terms of alpha RY0, so we can substitute and we can calculate this value of variance as 1 minus alpha square into RY0. So from this equation, it can be safely concluded that for the first order case, both the linear production and air methods yield identical values of the parameters to be estimated. Now let's see another model, that is second order Markov model. So this is in this we are taking two parameters, alpha 1 y of n minus 1 plus alpha 2 y of n minus 2. This should be y of n minus 2 plus epsilon 2 n. Using the same procedure, we can write two equations in terms of model parameters alpha 1, alpha 2, and they can be estimated by solving these algebraic equations. So it will be alpha 1 ry by 0 plus alpha 2 ry by 1, that will be equal to ry by 1, and the second equation is alpha 1 ry by 1 plus alpha 2 ry by 0, that will be equal to ry by 2. So further, the mean square error can be computed as sigma epsilon 2 square is equal to ryy0 minus alpha 1 ryy1 minus alpha 2 ryy2. That is equation number 16. So we can observe that by solving the set of equations number 15 and 16, the model parameters of the second order Markov process as given by the AR method are identical to those we have seen in linear prediction method for a second order linear prediction filter. So proceeding in the same way, we can find the parameters for pth order predictor and or we can say a pth order AR process. So this, let's suppose this pth order predictor given by this equation is yn equal to beta 1 y of n minus 1 plus beta 2 y of n minus 2 up to beta p y of n minus p plus epsilon p n. So if we multiply again by y of n minus 1, you can get the equations in terms of autocorrelation function. So, of course, we have to take the expectation as well. So that will be ryy1 is equal to beta 1 ryy0 plus beta 2 ryy1, similarly up to beta p ryp minus 1. One thing we have to remember that here we are multiplying with y of n minus 1. So that will be if y of n minus 1 is multiplied with y of n minus 1. That will give the autocorrelation at time like 0. And accordingly we have to keep time like 1 to approximately. Therefore it is coming p minus 1. So also we can write in a compact form that ryy1 is nothing but summation m equal to 1 to p beta m ryym minus 1. So in journal, this we can write ryk is nothing but summation m equal to 1 to p beta m ryym minus k for k running from 1 to p. So this is a sequence of the fact that expectation of yn minus k epsilon pn vanishes when k is greater than 0, since past values of yn do not depend on the present values of epsilon pn, that is y of n minus k and epsilon pn are stochastically independent. So to obtain the noise power or variance, we can write the compact equation by multiplying both sides of equation number 17 and taking the expectation. So that will be again equal to ryy0 minus summation m running from 1 to p beta m ryym. Now if you substitute k as 1 to p in equation 19, so we obtain a set of linear algebraic equations as we have seen for order 2. Now we have to calculate these parameters beta 1, beta 2, beta t. We can derive from this by using different autocorrelation functions. So these equations are usually called the Euler-Walker equations. So we can solve this for beta parameters by simply inverting the coefficient matrix. So thus if we let this P matrix as a column matrix of all the beta parameters, and this R matrix is nothing but the correlation we can say parameters, and this is a diagonal matrix P. So from this we can calculate the parameters B as P inverse into R. So having thus obtained the parameter vector B, we can proceed to compute the noise variance, that is sigma epsilon p square, by back substituting the parameter values as we have done in equation 21, and we can solve for that. So for convenience we can use this equation. This is the same equation if we have that number of parameters, and from that how we can calculate this sigma epsilon p square. So you can use this matrix relation as well. So the idea behind using the higher order AR models, mainly the linear predictors, is to remove more and more sequential correlations contained in the signal, as you can see. So for this figure, it shows the pth order linear predictor, or we can say pth order AR process. So these y of n minus 1, y of n minus 2, all up to y of n minus p are the input part, and we are multiplying that with these beta parameters, and finally we are subtracting. So that is correlation canceller part. So if all the correlations contained in the signal are completely removed, then what remains of Yn is basically unpredictableness, and as such epsilon Pn can be constructed as white noise. Now we have some properties of the linear prediction filter. So it is a linear filter that attempts to transform the input signal into the decorrelated, we can say, white noise. This is done by adapting the filter to the spectrum, or we can say the autocorrelation function of the input signal. Then by increasing the filter order, more and more of the spectral information is extracted and expressed by the filter. And the other basic property is the removal of correlations from the signal, and it can be expressed as in time domain. The present value of the prediction error indicates the instantaneous degree of unexpectedness in the signal, and in autocorrelation domain the prediction error is decorrelated. Now this was the linear modeling of EEG signal. Now we'll discuss a little bit of about the non-linear EEG model. The objective of this is to introduce some established models for generating normal and subabnormal EEGs. These models are generally nonlinear. Some have been proposed for modeling a normal EEG signal and some others for the abnormal EEG signals. A simple distributed model consisting of a set of simulated neurons, thalamocortical relay cells and interneurons was proposed that incorporates the limited physiological and histological data available at that time. And the basic assumptions were sufficient to explain the generation of alpha rhythm, that is the EEGs within the range of frequency range of either 7 to 12 or 18 to 13 Hz. A journal nonlinear lump model may take the form as shown in figure in next slide. Now, although the model is analog in nature, but we can see all the blocks are implemented in a discrete form. This model can take into account the major characteristics of a distributed model, and it is easy to investigate the result of changing the range of excitatory and inhibitory influences of thalamocortical relay cells and interneurons. So this nonlinear model of one cortical neuron pollution that was suggested in early 1970s, and later it was extended to multiple coupled population for the purpose of seizure detection. So we'll discuss about this one neuron population model. This is a nonlinear lumped model for generating the rhythmic activity of the EEG signals. In this we have two functions that represent the excitatory and inhibitory postsynaptic potentials, that is HET and HIT, and we have a nonlinear function that is FV, and CKs are respectively the interaction parameters representing the interneurons and thalamocortical neurons. So these are the expression of the functions, postsynaptic potentials. Here A and B are the maximum amplitude and AB are the lump parameters. Mainly if we relate to neurons, so that is dendrite average time delay. And this we'll see in figure, this sign represents cell soma or axon hillock, where all the neurons are like getting accumulated, and CK are the average number of synaptic contacts, and PT is neighboring populations and it is a stochastic process, and we have average post potential that will be equalized as pulse density. And we'll use this function, nonlinear function fv, which is 2 e naught by 1 plus e raised to power r v naught minus v. So this is a figure, it shows a nonlinear model. So in this model there is a feedback loop, as you can see, including both the inhibitory as well as the nonlinear function and their interaction parameters C3 and C4. You can see this fv and this function, inhibitory function, this is HIT. Other feedback includes mainly you can see upper part, that is excitatory potential, and again nonlinear function Fv with the interaction parameters C1 and C2. The role of excitatory neurons is to excite one or two inhibitory neurons. The latter in turn serve to inhibit a collection of excitatory neurons. Thus, the neural circuit forms a feedback system. The input PT is considered as a white noise signal. This is a journal model, and more assumptions are often needed to enable generation of the EEGs for the abnormal cases. Therefore, the function Fv may change to generate the EEG signal for different brain abnormalities, means it can be changed depending upon the situation. And also the CK coefficients can be varied. Now we have, in addition, the output is subject to, in this, environment and measurement noise. So we have another model, that is local EEG model, LEM model. The noise has been considered as an additive component in this basically in the output. If you see, this noise component is there, which is added to the output, that is EEG signal. So this model used the formulation by Wilson and Cowan, who provided a set of equations to describe the overall activity and not specifically to EEG in a cartel of excitatory and inhibitory neurons having a large number of interconnections. Similarly, in this model, the EEG rhythms are assumed to be generated by distinct neuronal populations which possess frequency selective properties. So these populations are formed by the interconnection of the individual neurons and are assumed to be driven by the random input. So the model characteristics such as the neural interconnectivity, synapse pulse response, and threshold of excitation are presented by the LEM parameters. The changes in these parameters produce the relevant EEG rhythms. In this figure, the thalamocortical relay neurons are represented by two linear systems having, you can see, impulse response, this HET and HIT. HET is on the upper branch, as we can see here, and this inhibitory potential as represented as HIT. The nonlinearity of the system is denoted by, you can see here, FEV, which represent the spike generating process. So the interneuron activity is represented by another linear filter, that is HET in the lower branch. As we can see here, we have another filter which generally can be different from the first, and a non-linearity function. Here again we have FIV. So CE and CI, you can see in this figure, that represent respectively the number of interneuron cells and thalamocortical neurons. And notation E and I refers to excitatory and inhibitory respectively. The input PT is assumed to result from the summation of a randomly distributed series of random potentials which drive the excitatory cells of the circuit, producing the ongoing background EEG signal. So such signals originate from other deeper brain sources within the thalamus and brainstem and constitute part of the ongoing or spontaneous firing of the central nervous system. So in this model, the average number of inputs to an inhibitory neuron from the excitatory neurons is designated as CE, and the corresponding average number from inhibitory neurons to each individual excitatory neuron is CI. The difference between two decaying potentials is used for modeling each postsynaptic potential, as we can see here. So HE or HI, so HET is A times exponent minus A1t minus exponent of minus A2t. Similarly, B is exponent of minus B1t minus exponent of minus B2t. So here A, B, AK and BK are the constant parameters mainly which control the shape of pulse waveforms. And the membrane potential are related to the axonal pulse densities via the static threshold functions, that is Fe and Fi. So these functions are generally nonlinear, but to ease the manipulations, they are considered linear for each short time interval. Using this model, the normal brain rhythms such as the alpha wave are considered as filtered noise. The main problem with such a model is due to the fact that only a single channel EEG is generated and there is no modeling of inter-channel relationships. Therefore, a more accurate model has to be defined to enable simulation of a multi-channel EEG generation system, and there is still an open question for this, and this area remains for the research. So for some topics, you can refer the book by Rangaraj M. Rangayan, that is Biomedical Signal Analysis, a case study approach. So for now,